Ever since we first looked up at the night sky, we've wondered, haven't we? What is all this? Where do we fit in?
It's that fundamental human curiosity, isn't it? And our picture of the cosmos, well, it's changed dramatically over time.
It really has. And that journey, understanding our place, or maybe our lack of a central place, is exactly what we're diving into today. We're looking at Stephen Hawking's The Theory of Everything, The Origin and Fate of the Universe. Came out in 2002.
Right, and it's basically 7 lectures he gave designed to make these huge cosmological ideas accessible. Not easy, but accessible.
Exactly. So our mission here is to follow Hawking's own journey, his quest to answer the biggest questions. How did the universe begin? Where is it going?
And that ties into the search for the holy grail of physics, right?
Yeah.
The unification of physics. One single theory for everything.
That's the goal, a single framework from, galaxies down to tiny particles. And just before we jump in, remember, you are experiencing a unique two-host AI conversation powered by Google's NotebookLM for deeper, more dynamic book summaries. Okay, so let's start where Hawking does. Humanity's first real attempts to make sense of the universe. It seems almost quaint now, doesn't it, that Earth-centered view?
It does, but you have to remember, for thousands of years, that was the universe. Hawking points straight to Aristotle. Earth is stationary, the center, sun, moon, stars, they all circle us on these perfect spheres.
A very neat, tidy model, and very human-centric.
Extremely. It took until Copernicus, centuries later, to really challenge that in a big way, saying, hang on, maybe the sun is at the center. But even he thought the stars were sort of fixed nearby.
So a step, but not the full picture yet.
Not by a long shot. Then you get Galileo with his telescope, Kepler figuring out the maths of planetary motion. Each step pushed humanity further from the center.
It's like the universe just kept getting bigger and bigger, and our importance smaller and smaller.
Precisely. We went from being the point to being on a small planet, orbiting an average star, in one galaxy among billions. It was a radical, almost unsettling shift, based purely on observation and math. It forced us to really rethink our place.
That's a huge mental leap. So our cosmic address changed dramatically. But then Albert Einstein came along and changed our understanding of the address system itself, space and time.
How did he revolutionize things?
Right. Well, before Einstein, people thought of space as just, an empty box, and time as this universal clock ticking away steadily for everyone, everywhere. Separate things.
Seems intuitive enough.
Yeah, but Einstein showed that's not right. His theories of special and general relativity basically said space and time are linked. They form this four-dimensional space-time. Think of it less like a box and more like a stretchy sheet.
Okay, a stretchy sheet. So what does that do?
Well, massive things, planets, stars, they don't just sit in space-time. They warp it. They create curves and dips in that sheet.
Ah, so like putting a bowling ball on a trampoline? Exactly like that. And what we feel as gravity is just us, or light, or anything else, following those curves caused by massive objects. It's not some mysterious pull, it's the shape of space-time itself.
Wow. So gravity is geometry.
In essence, yes. And this completely changed the game. It meant space and time weren't just the background, they were active players, affected by mass and energy. This was crucial for understanding how the whole universe could evolve.
Okay, so Einstein gives us this dynamic space-time. Then Edwin Hubble looks up with his telescope. What did he see that blew everything wide open again?
Hubble's observations in the 1920s were, well, truly staggering. He was looking at distant galaxies, and he noticed their light was stretched, shifted towards the red end of the spectrum.
The red shift, right. What did that mean?
It meant they were moving away from us.
Yeah.
And crucially, the farther away a galaxy was, the faster it seemed to be moving away.
So everything is rushing away from us. Are we special again?
Huh? No, not quite. It means the entire fabric of space-time itself is expanding. Like raisins in a baking cake, every raisin sees all the others moving away from it as the cake expands.
Okay, I get it. The space between galaxies is stretching.
Precisely. And if you run that movie backwards, if everything is expanding now, it must have been much closer together in the past.
All the way back to a single point.
Exactly. An incredibly hot, incredibly dense state. That's a Big Bang. The beginning. It wasn't an explosion in space, it was the rapid expansion of space itself.
And is there evidence for this besides the expansion?
Oh, yes. The biggest one is the cosmic microwave background radiation, the CMBR. It's like the leftover heat, the afterglow from that very hot early state, now cooled down and filling the entire universe. Finding that was huge confirmation.
Incredible. We can actually see the echo of creation. So we've gone from Earth at the center to warped space-time to an expanding universe from a Big Bang. But then things get weird on the small scale, don't they? The
Yeah.
quantum world.
They really do. Quantum mechanics describes the universe at the level of atoms and particles, and its rules are, well, they're bizarre from our everyday perspective. The key idea Hawking focuses on here is Heisenberg's uncertainty principle.
Ah, the one that says you can't know everything precisely.
That's the one. You can't know both the exact position and the exact momentum, which includes speed and direction of a particle at the same time. The more precisely you measure one, the fuzzier your knowledge of the other becomes.
Is that just because our measuring tools aren't good enough?
No, and that's the mind-bending part. It seems to be a fundamental property of reality itself. There's an inherent fuzziness or uncertainty baked into the universe at its smallest scales. Things operate on probabilities, not certainties.
So not like clockwork at all down there.
Yeah.
How does that connect back to the big picture, like the early universe?
It's absolutely crucial for the early universe. When the universe was incredibly tiny and dense right after the Big Bang, quantum effects like this would have been dominant. You can't understand the beginning without quantum mechanics. And, maybe surprisingly, it also pops up when we talk about black holes.
Okay, so we have these two huge theories, general relativity for the big stuff, gravity and the cosmos, and quantum mechanics for the tiny stuff. But they don't quite mesh, do they? That's the drive for unification.
Exactly. Physicists want one theory that describes everything. Hawking explains the four fundamental forces we know. There's gravity, shaping the cosmos, then electromagnetism, that's light, electricity, chemistry, basically everyday interactions.
Okay.
Then there are two forces acting inside the atom's nucleus. The strong nuclear force holding protons and neutrons together, and the weak nuclear force involved in radioactive decay.
Four forces. And the goal is to show they're all related.
Yes, different aspects of one single superforce. And there's been progress. They managed to unify electromagnetism and the weak force into the electroweak force. That was a huge win, showing it could be done, at least under high energy conditions.
But bringing in the strong force, and especially gravity, that's the hard part.
That's the major hurdle. Finding a quantum theory of gravity uniting general relativity and quantum mechanics is the biggest challenge. It's that search for ultimate understanding. This kind of exploration, trying to find the underlying patterns, it really inspires reflection and rational thought. It reminds me of the kind of analysis we aim for on Mindful Moments, our YouTube channel, looking at books through an AI lens.
A great point. That quest for unity is powerful. Now, you mentioned black holes earlier, and they seem like places where these extreme theories, gravity and quantum mechanics, might collide. What exactly are they?
Black holes are fascinating, truly extreme objects. Hawking explains they form when a really massive star runs out of fuel. Its own gravity becomes overwhelming and it collapses catastrophically.
Crushes itself down.
Incredibly so, down to a point of infinite density called a singularity. Around this singularity is a boundary called the event horizon.
The point of no return.
Exactly. Once anything crosses the event horizon matter, light, anything, the gravity's so strong it can't escape. It's pulled inevitably towards the singularity. For a long time, that was the picture. Black holes just swallow things forever.
Utterly black cosmic vacuum cleaners.
But Hawking had a revolutionary idea about that, didn't he? Something that changed everything again. He absolutely did. This was perhaps his most famous and profound contribution. Everyone thought black holes were completely black, endpoints. But Hawking applied quantum mechanics near the event horizon.
Okay, but for the quantum fuzziness into it.
Right. He realized that because of quantum effects, specifically virtual particles popping in and out of existence in pairs near the horizon, black holes aren't entirely black. In a way, yes. Sometimes one particle from a virtual pair falls into the black hole while the other escapes, carrying energy away. To an outside observer, it looks like the black hole itself is emitting radiation, a faint thermal glow. We call it Hawking radiation.
So black holes radiate heat.
Yes, very slowly for large ones, but they do radiate. And this means they lose mass, they lose energy over incredibly long timescales.
Wait, if they lose mass, do they eventually disappear?
That's the stunning implication. Especially for smaller black holes, they would radiate faster and faster and could eventually evaporate completely in a final burst of energy.
Wow. So black holes aren't eternal prisons after all.
Apparently not. And this raises huge questions about what happens to the information that falls into them, about entropy, about the ultimate fate of things. It connects quantum mechanics, gravity, and thermodynamics in a completely unexpected way. It didn't provide all the answers, but it opened up a whole new realm of physics.
That is truly mind-bending. So Hawking is dealing with these incredibly complex ideas, yet the theory of everything was a massive bestseller. How did he manage to communicate this stuff so effectively?
He had a real gift for it, didn't he? Despite his physical challenges, part of it is the structure the 7 lectures build on each other logically. He starts with familiar ideas and gradually introduces the more complex ones.
Takes you step by step.
Exactly. And he uses humor. There's a wit there that makes it less intimidating. But his real genius, I think, was his use of analogies.
Like the bowling ball on the rubber sheet for space-time.
Perfect example. He could take an abstract mathematical concept and give you a visual and intuitive way to grasp it, even if you didn't know the equations. He deliberately avoided complex math in the book, knowing it would put people off, even though he stressed that math is the language the universe is written in.
So it's accessible, but not dumbed down.
Not at all. He respects the reader's intelligence. The core themes are always there. This human drive to understand, the interplay of theory and observation, the search for that ultimate unity. He makes you feel like you're part of this grand scientific adventure.
And clearly, that approach worked. The book's impact was enormous, wasn't it?
Oh, absolutely massive. It brought cosmology and theoretical physics to a huge general audience, people who never thought they could understand this stuff. It really cemented Hawking's status, not just as a brilliant scientist, but as one of the greatest science communicators ever.
It helped democratize these big ideas.
Definitely. It inspired so many people, sparked curiosity, and probably led quite a few down paths in science. You know, finding ways to explore these complex topics is something we try to continue, both on Mindful Moments and through our other deep dives like this one.
So as we wrap up, maybe the thought to leave people with is this. Hawking takes us on this incredible journey towards a theory of everything. But maybe the theory isn't just the destination, the final equation.
What do you mean?
Maybe the real theory is the journey itself, the ongoing human quest to ask questions, to observe, to push the boundaries of knowledge, even knowing that every answer seems to just lead to deeper, more fascinating questions.
That's a beautiful way to put it. The curiosity, the process, that's the constant.
Indeed. To dive even deeper into the intricacies discussed today, click the link on screen for the in-depth book critique.
And subscribe to our show. Share this deep dive with fellow curious minds. And maybe consider purchasing the book via our link.
And always think rationally.